Hi, my name's Bill Kennedy with Arden Labs, and today I'm going to show you some of the cool tooling that Go has and some of the reporting as well. And to show you that, I'm going to look at a piece of code and we're going to profile it. We're going to do some fun with it. But the cool part is there's a little story behind this piece of code that I want to get to you, share with you as we go through it. So let's kind of look at the code and we'll start. So back in the day, maybe 2015, 16, when I was first learning Go, I started in Go around 2013. I was getting a little better by 15, right? And I decided that one day I wanted to learn how the IO package worked. This was a package that everybody was talking about how great it was. But I'd never tried to solve problems with data streams. So I never got a chance to play with the package, and therefore I had no idea how to use it. And I mean, I've taken everybody's word for it that this package was great. So I wanted to learn it. So like with anything, when you want to learn here, you got to have a problem to solve. And so I figured out a problem to solve. I decided that what I was going to do is scour the internet for Elvis, the king of rock, Elvis's name, and anytime I found it misspelled. In other words, anytime I found it spelled starting with a lowercase e instead of a capital E, well, I was going to fix that, damn it, because this is the king. The king can't have his name spelled without that capital E. Now, obviously, I can't test this against the entire internet. So my idea first was to build a little data table of input and expected outputs so I could test the code that I was going to write. And so here we've got this little data table. On the left-hand side is the input. On the right-hand side is the expected output. If you look on line 24, you'll see how I'm expecting to have Elvis's name capitalized. And you can go through that table and see what I'm expecting to be able to achieve with my algorithm. And then just to make this kind of fun, I wrote a couple of functions that assemble the input and the output into a single stream. And then I went ahead to write my algorithm. Now again, I've never ever done this before. I had no idea what I was doing. So I had a general idea. This is my actual first draft of code in trying to solve this problem. And the idea was this. Okay, I was going to take this buffer and I was going to find the length of bytes we were looking for there on line 86. There were 5, and I was going to create a buffer of 5 bytes. That's what I'm doing on line 89. And then on line 93, I read in the first 4 bytes out of the stream, and then I go into an endless sort of loop here where I read the 5th byte out of the stream, attach it to the end of my buffer, and then I compare what I have in the buffer with what I'm looking for there on line 109. If I find it, I write out the replacement string, which is Elvis with the capital E, and then I read in the next 4 bytes again. If it isn't a match, then I just take that byte I just read, put it out into the stream, and then I kind of slice that byte off the buffer. So when we come back to the top of the loop, I can add the next byte from the stream into the buffer and do it all over again. So you could just imagine a buffer of 5 bytes, and I'm chopping off the front, adding to the back, check, off, check, 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 check. Cool, 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 cool. Okay, so I wrote this little algorithm. It took me about 20, 25 minutes to write. And it worked, and I was super excited. I mean, I solved this problem. I'm ready now to fix Elvis's name all over the internet. But, this was my first draft, and I was kind of curious how others would solve this same problem. So I sent a tweet out over the internet, right? So I went on Twitter, sent a tweet, and I asked everybody, hey, how would you solve this same problem? And I got a bunch of solutions back, but my favorite solution came from my friend Tyler. Tyler wrote what I call algorithm 2. It was really, really cool. Now, Tyler knew he was only reading these bytes, so he started with a new reader, and he also looked at the length there on line 137. But then he did something sort of cool. He didn't use a buffer per se. What he did is he read that byte out of the stream there on line 145, and then he compared that byte with the index position of that string that we're looking for, that find. So if you look on line 140, index is 0. So we check B with that letter E, right? Find is Elvis, lowercase. And if it matched, then he would increment the index, and then he would look to see if we've incremented this index 5 times in a row. If we did, we found our match. That went out, we fixed it, and then we started over again. And if we didn't find a match, right, then what we would do is send that byte out, right? We unread it out of the stream, we start it again. It was really genius. The whole idea of just reading one byte out of a time, comparing it against the find, against an index position. If we incremented it 5 times, we found it. I thought it was awesome. So I call up Tyler and I say, Tyler, have you at all benchmarked your algorithm? Because, you know, I've got my algorithm, you've got your algorithm. He said, no, Bill, I haven't benchmarked this thing. And I say, okay, cool. What I'm going to do is write some benchmarks, and I'm going to see how your algorithm now compares to mine. He said, great, Bill. Once you do that, let me know. I'd love to hear the results. So I went ahead and I wrote an _test file here. And I wrote 2 benchmark functions that I wanted to use to compare these 2 algorithms. So we've got algorithm 1 and we've got algorithm 2. Now, right before the benchmark functions, where I assemble that input stream, I got my find, I got my replace, I got my buffer, and we loop. Now, if you've never seen a Go benchmark function before, it's actually really cool. And they made it, I think, fairly reasonable to understand. So you write a function that starts with the word benchmark, it takes the testing B pointer, and then you have this special loop that iterates from 0 to B.n. And throughout this loop, we're going to be executing that code that we want to benchmark over and over and over again. And there's settings here. By default, this loop will run for 1 second. So the benchmarking tooling is trying to sort of set a clock underneath the covers, and it starts using different versions of B.n to get to that 1 second mark. So it might run through this loop several times to figure out what value of B.n gives you 1 second. We're going to run with 3 seconds, but you can also tell the tool specifically how many iterations you want. You got to play with this sometimes, because sometimes your function is quick, like ours is going to be today. I've seen functions that take maybe 20 seconds to run, and you know, it all depends on what you're trying to accomplish. But you know, I think as a general rule, the more iterations that you can have, the more accurate the results should be. So here we are. Here's our benchmark functions. Benchmark 1, benchmark 2, and I want to run these benchmarks and get a general idea of how these 2 algorithms work. Now, just to save some time here, I'm just going to copy and paste just a little bit of this for a second here. I'm going to go into my terminal window. Okay, so I'm already in the folder where this is. And so what I'm going to do is run our bench. So we're going to say go test, and then we're going to use the bench flag with a period to say run all the benchmark functions that you see. And as you can see here, I copied and pasted a dot somehow. So we're going to do it again. There we are. And if you see here, the test ran. Now, I didn't really even set the bench time. Let's do that now. Bench time to 3 seconds, just so, you know, I feel like it runs a little bit longer. And I'm going to run it twice at 3 seconds, just to make sure the machine is warmed up and everything's good. You can see when I set the bench time to 3 seconds. Well, I'll tell you what these numbers are. You can kind of see the difference too. Okay, so you can see there's algorithm 1 and algorithm 2. And this number here represents the number of iterations that we executed to get our time. So in this case, we executed that loop, what is that, 3 million times. You can see when I did 1 second, it was only 1 million. So we got an extra like 2 million iterations here. You can see that algorithm 2, however, runs about 11 million iterations. And that's because it's just faster. I mean, we can see that it's faster right here. We can see here that I'm running at about 1.1, 1.2 microseconds, and Tyler's algorithm is sort of sub-microsecond. Okay, so I'm looking at these results and I'm like, wow, I mean, Tyler's almost like 3, almost 4 times, let's just say he's like 4 times faster than me. Whoa. So, you know, I'm impressed. I think it's kind of cool, but I want to really start to understand, why is Tyler running so much faster than me? So one of the things that I can do almost immediately is get a sense of what's happening with memory, right? Maybe by looking at memory, I can start to analyze a little bit why he's 4 times faster than me. So I can do that fairly quickly here by adding a switch here called benchmem and say, show me the memory allocations that are happening as well. All right, so we're gonna run for those 3 seconds, and we're seeing, I'm running that 2.8 million iterations there, 10 million iterations this time. And I've got some more numbers. Tyler's still 4 times faster than I am. But now I'm learning a little bit more. You see, what this is telling me is that there are 2 allocations happening per operation, per call, worth a total of 53 bytes. And Tyler, well, he wrote a 0 allocation algorithm. Whoa! When I see this, I'm like super excited. I mean, nobody writes a 0 allocation algorithm out of the box. So I called Tyler up right away. I'm like, dude, do you know that you wrote a 0 allocation algorithm and you're like beating me by like 4 times? Dude, you're amazing, man. And so we're on the phone. I'm really excited about this. We're laughing a little bit. And I hang up the phone and all my excitement turns to sort of despair. I'm starting to think, I teach this stuff for a living, and look at what Tyler did to me. And I love my algorithm. I mean, I really love the work I put into it. This is no good. I think now that Tyler has thrown down the gauntlet, and now I'm determined to make sure that I'm determined to make my algorithm faster than Tyler's. Now, this is all nice and dandy, but like, where do I begin? All I know right now is that Tyler's written a 0 allocation algorithm and I haven't. And so maybe, just maybe, if I can get rid of these allocations, these 2 allocations worth 53 bytes, maybe that's just enough to get my performance, if not equal, but better than Tyler. The key, though, is I've got to figure out where these allocations are coming from. That's no problem, though. There's no problem, because I can add the memory profile switch and give it a name for a file, p.out. And what I can do here is say, hey, write a memory profile of the code that we're benchmarking here. Okay, cool. So we're going to run it again, and yeah, I got to watch Tyler beat me again, but we're coming after Tyler. Tyler, we're coming after you, dude. Oh, yeah. Okay, so nothing really has changed here. But you can see now that I've got a p.out file, and this is really what I want to go after here, p.out. You'll also see that the test binary, memcpu.test, was left over. And they do that because you could leverage this binary with the profiling to go a little bit deeper. We don't need that today. I just need the p.out. And what I'm going to do now here with the p.out is go tool pprof, 2 p's, p.out. This is all I need to do here. Okay, now I'm in this interactive terminal-based command line tool. There is a browser version of this, but I like to I'll show it to you a little bit, but I kind of like to stay here. And again, what I'm doing is trying to figure out why my algorithm, alg1, has those memory allocations and where they are. So to do that, I can run a list command, and I can say alg1 list, and the tooling will find my function from that profile data and start to give me some information. Now, there's a couple of columns of numbers here to the left of the algorithm, and you can see here that these are the 100% of all of my allocations are right here. There's a flat column and a cumulative column and numbers on both sides. So what is this telling me? Well, let's start here on line 83. This is telling me that I have an allocation happening on line 83. It is cumulative only, which means that the allocation's not due directly to this line of code. It's due to some code that's inside this function call to new buffer. However, the allocation on line 89, remember I said 2, here they are, well, that's flat, which means that this code itself, this specific line of code, is causing the allocation. So I've got this cumulative only allocation, something's happening inside a new buffer, and then I've got this flat, right? All allocations eventually have to be flat. And what we need to do is sort of try to find where the call to new buffer, when that eventually sort of goes flat. Okay. Now, a profile is great at showing us where, right, in this case, kind of where things are allocating. What is allocating? What it's not good at is telling us why. We have zero clue, and I don't like guessing. Now, here's something cool about Go. The compiler runs something called escape analysis. And the escape analysis is determining when a value ends up on the heap instead of being on the stack. That's an allocation. An allocation in Go is when that value, when it's decided by the compiler that that value will be allocated on the heap, because that's when we need garbage collection to get involved. If that value can stay on the stack, that's a sort of a self-cleaning mechanic. And so we need to ask the compiler why it's chosen somewhere down this call path to create an allocation. And we can get that information from the compiler as well. Let me exit this for a second and go back to our benchmark. Now, when we run this benchmark, one of the things that has to happen is the compiler has to compile and build that test binary before running it. So this is kind of cool. I can say GC flags m equals 2. What I can do here is say, give me a level 2 escape analysis report, please, about the code that you're building. This should give us the why of those 2 allocations. All right, let's run that. A lot of stuff flashed past the screen. We'll interpret that as soon as we can. I have to watch Tyler beat me one more times, but we're coming after you, Tyler. It's going to happen. And now what I can do is go back into my profile and list algorithm 1, and I have everything I need now inside my terminal to figure this out. Okay, let's start on line 83. Now, this is in a file called stream.go on line 83. So one of the things I can do, and why I like to stay in this terminal, is I can go to my find. I can put stream.go line 83 and look at all the 83s that are going on. And the very first thing we see is inlining call to new buffer. What does that mean? It means that we're not actually making a function call on new buffer. This is really, really odd, because if we're not making a function call to new buffer, then there's no way that this allocation could be cumulative, because there's no call being done. Now, let's talk a little bit about what this inlining is. The inlining optimization is one of the most important optimizations in Go. And with every release of Go, just about, there's improvements that are done with the algorithms, the escape analysis algorithms and the inlining algorithms. And these things really help with performance, because if you don't have to make that function call, then you don't have to set up the stack. You don't have to do a bunch of things that take time. So let's take a look at the code real quick on line 83. So here's line 83 right here, right? And as we said, that there's an allocation happening, at least the tooling is reporting it's cumulative. Why don't we go in and look at what this function call does? Now, if you look here, what we could see is this is what I call a factory function. It is constructing a buffer. That's all it really does. It constructs a buffer, and it returns it back to the caller using pointer semantics. In other words, it says construct and then share. Now, one of the things that happens when you construct and share up the call stack is the escape analysis algorithm has to do an automatic allocation of that. That's automatic. You can't put that on the stack and then unwind it, right? Because that memory is going to be reused again. And so it looks like what the tooling is telling us, at least from an allocation standpoint, is that there's an allocation going on here, because when we call the function and we do this construction and we share it back up, that has to be an automatic heap allocation. So we see that, right? But what the inlining is doing is it's saying, no, we don't want to make this call because we know it will be an automatic allocation. So let's inline the code, or in other words, take the code out of the function and just inline it here. And so in other words, what would happen is the function call would go away. The construction of the value happens here, and that would essentially eliminate the allocation. Now, the allocation isn't eliminated. At least that's not what we're seeing. Now, let's take a look at Tyler's algorithm for a second. Do you notice that Tyler, instead of calling new buffer, he's calling new reader? And if you were to look at this, you would also see that it's just a factory function constructing and sharing back. And so the question is, why did Tyler get that non-allocation and we didn't? Well, I would bet that Tyler also got an inlining optimization there. And so the call isn't being done. And for some reason, Tyler's not doing anything that causes the value to allocate, but we are. So this is super confusing because our report here is saying that the function call was done. This is saying, hey, Bill, the function call was made and that value got allocated because you shared it up. And then the escape analysis report says, no, Bill, it wasn't done. We inlined that. So what's wrong here? What's wrong here, and I think it's a bug, though I can't get the Go team to fix it, is that when we run this report using the terminal, it puts it in a mode where it says ignore any inlining optimizations. Now look at this. If I do weblist alg1, this is the browser version of the same report. And what does the browser version say? It says, no, Bill, it's a flat allocation. Look, it's flat. So when I'm in the browser version of list, it is saying, okay, I will assume inlining, or I will show inlining optimizations. There it is, it's flat. But when I'm in the terminal, it decides that it's not going to do that. Let's put this code back. I saw that in the output that was kind of funky, right? It was reading this code. Now, how do I get the terminal to do this? Okay, I can get it to actually do this if I use a switch called no inlines list alg1, boom. Now, it's counterintuitive because this flag is supposed to turn off inlining, and it will on the browser side, but in the terminal side, it actually turns it on. No, don't ask me. I've mentioned this a billion times. But now we see that it's flat. Okay, how cool is that? So now our output here in our list command is showing that this is flat, and we're seeing here that there was an inlining optimization done. So this function was actually never executed directly. Its code was brought into our function, but yet there's still an allocation. So there's something that we're still doing in this code that Tyler isn't, even though we both got that optimization. Well, let's keep looking at the report. Okay, here's more about line 83. And sure enough, it's saying that we're escaping to the heap, and I'm looking, and I see this. Whoa. It says, on line 113, there's some interface conversion going on here. Line 113. Okay. Let's go back to our code and look for line 113. And it's the last call of read full. which would mean that all the calls of read full would sort of do this. And we can see the report is reporting about this last call. Now, why is this function call causing an allocation for input, and where's this interface thingy-majig? Well, take a look at this function. The whole reason that I even went down this path was to play with this IO read full. But if you look here, the first parameter to read full is an interface. And unfortunately, anytime we store a concrete value inside of an interface, that is going to be an automatic allocation unless the compiler can find some edge cases where it can decide to like throw the interface away and it knows that everything's safe. We are not getting any of those sort of edge case compiler sort of optimizations here. So essentially, when we pass input into the read full function, which we do 3 times, that's causing the concrete input value to get inside the interface, which is causing the allocation. Now, if you look at Tyler's algorithm, notice that he doesn't use the IO package. He's using the method set off of the concrete type. And even though the method set is using pointer semantics for the receiver, everything is being shared down, not up. So essentially, if we want to get rid of this allocation here of input, we have to stop using the IO package, which was the whole reason we started this entire exercise. But I'm at the point now where I want to be at least as fast, if not faster than Tyler. So guess what? I don't care about the IO package. What we need to do is replace these IO calls. Now, what's kind of cool is that input has the same sort of method set. Here's a read call. And we could essentially steal this code here. It also returns the number of bytes and an error. So look, that call is the same as this call. So I just got rid of 2 of them. Now this one's a little tricky because we're attaching it to the end of the buffer. And I have to do a couple of things to make that happen. So I have to do input read byte, but notice that read byte returns the 1 byte, which makes sense. So I'm going to tell it to put it at the end of this buffer. And then what I can do is the same thing here. All right. All right. Or I can do this. If error not equals nil, we'll just get rid of this. There we are. Okay. And so what we got here, and you can see here that I'm, that's my problem right there. What are you doing, Mr. Kennedy? You can't use short variable declaration operators. We have values that already exist. Okay. And so look what we're doing here now. I'm using the method set for to read the byte and to read, and I got rid of all of the IO calls. This should get rid of that allocation because we're no longer trying to store input inside the interface. Okay, let's see if we were successful in doing this. Let's exit, let's clear this screen. Let's think about what we need to do now. So I need to run my benchmark again. Let's do it. Got my escape analysis. There it is. Ooh, look at that. Look at that. We're down to 1 allocation worth 5 bytes. And now Tyler isn't even what? I mean, almost just twice as fast as us. That's it, right? I mean, just rounding numbers here, right? It's just, we went from 4 times to that, 2 times. So now what? Okay. Maybe we get really lucky and get rid of this last allocation here. So we've run the escape analysis. We've got the report. We go into our pprof. We list algorithm 1. And there it is, line 88. Okay, so let's go now to stream line 88. And what is the report telling us? There it is right here. It says non-constant size. Okay. So here's another thing about the escape analysis algorithm. If the compiler doesn't know the size of something at compile time, well then it has to put it on the heap. All of the stack frames are fixed in size at compile time, so they're not dynamic. So if the compiler doesn't know the size of something, guess what? It's got to allocate. Now, if we go back to line 88, we can see what's happening here. When we construct this buffer of 5 bytes, we're using the variable size, not a literal value. So it doesn't know, but Bill, we need to use the variable because, right, maybe we want to find something else. Okay, well, how about we do this? If you promise not to tell Tyler anything, I could just do that right now. Yes, this is a hack, but if you promise not to tell Tyler, I promise not to tell Tyler. So now the compiler will know the size of this buffer at compile time. I only care about Elvis, so we should be fine. Okay, let's see what happens here. I'm going to run our benchmark again. Okay, give me, oh, there we are. We are now a 0 allocation algorithm, except Tyler's still faster than us by about 200 nanoseconds. Okay, but you know what? I'm not giving up. Come on, now you don't want to give up. We got so close just getting rid of these 2 allocations. Well, Bill, what more can we do? What more can we do? Well, guess what? We were looking at a memory profile. Now it's time to look at a CPU profile. We use the CPU profile, maybe we'll find something in our algorithm that we can just tweak. I don't want to change it, right? Just tweak it. So let's run it again. Here we are. We can see that we got 0 allocation, still beating us by about 200 nanoseconds, but that's okay. Go tool pprof, p.out, let's do it, list algorithm 1. Boom. Now, we can see here that we've got 430 milliseconds of flat time, 4 seconds of cumulative. Got to go after the biggest piece of this pie. So let's look for that. And it looks like half of that time is right here on equals. And there's some time there on output. So what I'm learning is that if we really want to get to Tyler's performance now, we've got to focus on this bytes.equal. We can replace this in some way. We'll probably be at least as fast as Tyler. However, with all that being said, the difference right now is 200 nanoseconds. What am I doing? In fact, what should I have done 40 minutes ago? I should have just used Tyler's algorithm because it's better than mine, man. What am I doing? This is where we got to worry about going down these rabbit holes, right? It was kind of fun to analyze what was going on with the memory profiling and to find those lines of code and to be able to, identify through the escape analysis report what was wrong and tweak the code and watch those allocations go away. And it was brilliant. But at the end of the day, like we were talking about nanoseconds of difference, and now I'm down to 200 nanoseconds of difference, and I'm looking to start changing algorithms. I'm going crazy here. But I love the tooling here. How cool is the tooling here in Go, where it will allow you to sort of dig into your program and see what's going on. I just recently did this for some client code that was like going crazy allocations. And we identified that some code that they wrote was using a buffer size of 1. 1. All this reporting allowed me to see all of that. And then when I saw that, I was like, wow, okay, there it is. We changed that buffer to 32K and performance came back. But it's this tooling that allows us to see these things. It's this tooling, once you learn a little bit, that lets you begin to analyze. But you got to have a program that's running before you can even play with this. So hopefully you've enjoyed some of this. You got to see some more cool tooling that's coming out of Go and gives you an idea of how you can use benchmarks and profiling to get a sense of how your program is doing and even find ways to improve it.